Let's take a look at a few examples of conservation of momentum and impacts. So we have two balls here. They have a mass MA and MB. And if the direction of motion is right along the line of the mass centers, we call that a central impact. So we have a central impact here. So what we do for conservation of momentum, the left-hand side of the equation is prior to impact, and the right-hand side of the equation is after the impact. So on the left-hand side here, we'll have MA, velocity of A at time 1, plus MB times the velocity of B at time 1 is equal to after the impact, which is MA, the velocity of A at time 2 or state 2, plus the mass of the ball B times the velocity of B at time 2, state 2. Okay. All right, so this is the equation that we have here. And central impact, let's make sure that we're getting the sign conventions right, because in these 1D problems, it's very easy to get the sign convention wrong. So we have here, we're going to call positive to the right. So VA is 1 meter per second here. And then we have VB1, which is going to be prior to impact, but it's actually to the left. So we need to put a -2 in there. Okay. The right-hand side of the equation, we still have the same thing. And with just this given, we can't really formulate how the velocity is going to be affected after the impact. We need more information, and we'll get to that in a little bit. Okay, so let's take an example of this. Okay. So the next example is a little more complex. And what we have here are two balls, and the motion is not aligned with the line of impact here, as you see the line of impact across here. So this is the line of impact. And this is what we call an oblique impact then. So how do we solve a problem like this? Well, we need to do both the X direction and Y direction. So the conservation of momentum must apply both to the X direction and Y direction. So in the X direction, right, we would have on the left-hand side prior to impact, we would have the mass of A times the velocity of A at 1, which would be VA cosine 45. And then we would have the mass of B times the velocity of B, which will be in the negative. The component of that in the X direction will be negative. So we have negative VB cosine 30 degrees. Okay. And then the right-hand side, then we would have MA VA 2 in the X, and then plus MB VB 2 in the X direction. And then we could do the same for the Y direction as well, right? Using our cosine and sines here to do conservation of momentum in the Y direction. So that will give us two equations that then we can solve the problem. As I mentioned in the example above, even if we knew the masses of these two objects, we wouldn't be able to determine the velocity of A and the velocity of B after the impact without more information. And the information that we need is kind of how much do these balls stick together after they come in contact with each other, or how much do they repel each other after they come in contact with each other. And that measure is actually called the coefficient of restitution. So coefficient of restitution. Okay. And the coefficient of restitution is a measure of the relative velocities before and after the collision. So for example, we use the letter E for the coefficient of restitution, and it is equal to the velocity of B after the collision minus the velocity of A after the collision. Let's get that right. After the collision, divided by the velocity of A before the collision minus the velocity of B before the collision. So let's take a look at what this actually means, right? So if the velocities are very close to each other after the collision, right, this top numerator number becomes very small. All right, so if they're moving together, this number becomes very small on the top. So what we call that is a plastic impact. If E is equal to 0, we call that a plastic impact, meaning that they stick together after they come in contact with each other. The opposite is if E is equal to 1, right? E is equal to 1, that means that is elastic impact. That's what we call that case. And for an elastic impact, right, the relative velocities before or after the collision are equal to the relative velocities before the collision, all right? So the top number and the bottom number are equal to each other, okay? So those are the two conditions, and for all impacts, it's going to fall somewhere in between 0 and 1, all right? So how do we analyze this situation? Well, we only use this formula along the line of impact here. So let's go back up to this example where we have an oblique impact, right? The coefficient of restitution then, right? The line of impact here, if we have our coordinate system as x and y, the coefficient of restitution then will be used along this x-axis here because that is the line of impact. So the coefficient of restitution is VB 2x minus VA 2x in the x direction divided by VA 1 in the x direction minus VB 1 in the x direction. So this equation only applies in the x direction because the line of impact is there. And there's another homework problem that goes through this that I have the solution for, 1574, I believe. And you can look at that for an example of how to solve these equations with the coefficient of restitution.